Farther and higher is the Olympic motto. And successive generations of aircraft constructors have pursued similar goals with all the means at their disposal. The Focke-Wulf Condor was flying non-stop from Germany to the United States as early as the late 1930s. The last propeller-powered aircraft to see service with Lufthansa was the sleek Lockheed Superstar, which represented an aviation milestone. The very first generation of jet-propelled machines flew even faster, higher and farther. Approaching the speed of sound, they could bridge the void from continent to continent, from country to country, from city to city. Though the market still demands wide-bodied, long-haul aircraft like the DC-10 and the Boeing 747, the introduction of the Jumbo meant the end of the old style of optimization for the foreseeable future. Speed and size were no longer paramount considerations for the designers of the new Airbus aircraft. For the Airbus A310, concepts such as fuel economy, low operating costs, and environmental compatibility became design objectives. The new Airbus was to be quieter and more economical than any comparable aircraft before it. Because Lufthansa was one of Airbus Industries' first customers, the airline was able to contribute some of its own technical and operational know-how during the development stages. The fuselage of the proven A300 was retained almost unaltered. The cockpit and wings had to be redesigned to comply with the latest technological developments. Modern construction methods were a decisive help. But in spite of ultra-modern design and construction methods, the mock-up was made of wood. The saw and the rasp went into action just as in the pioneering days of powered flight. This material was used to construct parts that later would be made of metal. Would the various elements fit? Was the design right? Wood and chipboard provide insights for series production. There were further design problems that couldn't be solved on the drawing board, even with computer assistance. Fitting the intricate tangle of conduits in the narrow trailing edge of the wing had to be tried out in actual practice. This is the only way to simulate actual maintenance situations. In flight operation, a single conduit occasionally has to be replaced without having to strip down half the wing. The mock-up pipes are bent by hand with the aid of a vise. The curves and bending angles of the pipes can then be mechanically scanned and digitally stored. The program data is used to manufacture a hydraulic conduit by automation. There's no blueprint, just a handmade template. Another wing mock-up, suspended vertically, undergoing wind tunnel testing to check its airflow patterns. A miniature turbine powered by compressed air blows its exhaust close to the landing flap. This test provides insights into the aerodynamics of the relatively slow landing approach flight. The new wing and the improved engine interact reciprocally. Exhaustive test series pave the way to minimum drag, maximum lift, and optimum fuel economy. Flow rates and their effects are also the subject of this test. Today's airline passengers demand draft-free air conditioning irrespective of whether the air has to be heated in northerly latitudes or cooled at the equator. The A310 is fitted with a high-performance air conditioning system which circulates air at exactly the right temperature, and the passengers are not even aware of it. As testing goes on in the design department, workshop construction programs are already being started up. These, for example, are the assembly jigs for fabricating the wings in Great Britain. Investments in the multi-million bracket. Automation is an integral part of modern aircraft subassembly methods. There's no other way to achieve the precision demanded in the sub-millimeter range. Complex shapes are milled down from 20-meter-long arm-thick alloy plates. The proportion of waste may be high, but structural advantages result from machining parts in one piece. At British Aerospace in Chester, a wing box is manufactured. The drilling and squeeze riveting machines, which are used to mate the wing skin panels to the stringers, are excellent examples of modern automated production technology. The airframe fitter's responsibility is to keep a watchful eye on things. This data-controlled machine automatically sets 15,000 rivets per wing. It drills a hole, countersinks the rivet head, inserts the rivet, squeezes it, and finally mills the surface. The preformed panels are moved by gantries to the assembly jigs, where the ribs have already been positioned. The further the production process advances, the greater the proportion of manual work involved. Anything up to 8 wing pairs leave the assembly jigs every month. The new wing shape, with its characteristically curved section and thick wing body joint, generates greater lift with less drag. Translated into economic terms, this means reduced operating costs. Lightness is paramount, so many elements of the secondary structure are made of new space-age materials, such as carbon fiber reinforced composite. They are tough and even stronger than steel. Carbon fiber components are 25% lighter than metal ones. They help to save weight, thus reducing fuel costs or allowing for higher payloads. The spoiler gets its shape from profiled honeycomb panels. Several layers of woven synthetic fiber cover the spoiler body. It is given the required strength by the crisscross pattern of the various layers. Final wing assembly in Bremen. You have to look very closely to notice the difference between the two Airbus wing designs. But between these two shapes, there are 10 years of development. The airframe fitter no longer has to move from job to job with his tools. The wings are transported to his workplace on air cushions. Each wing box, delivered from Chester, is equipped by Messerschmitt Boko Blohm with flaps, slats, ailerons, air brakes, and their associated actuators. The automatically produced piping fits exactly into its place in the trailing edge of the wing. Dealing with the vast number of components demands precise logistics. That means the right parts in the right location at the right time. Fitting a spoiler. It's hard to tell that it is made of high-grade composite. A minimum of moving parts means easier maintenance. so the landing flaps were designed as a single unit. The flap is over 10 meters long. A functional check is carried out once assembly has been completed. All moving parts have to be tested. The hydraulic systems are in triplicate. Each independent system could actuate the control surfaces in an emergency. At Messerschmitt Bölkow Blohm in northern Germany, the Airbus A310 fuselage takes shape. Riveting the body segments has been largely automated. Assembly line production in aircraft manufacturing. 8 body segments go to make up the fuselage section. The body is in fact a hollow tube surrounded by an astonishingly thin skin of sheet aluminium alloy, only about 3 millimeters thick. The fuselage acquires its stability from the frames and stringers, as well as from the floor which will later carry the seating. The individual body sections are riveted together. Rivet after rivet is driven with utmost precision. Building aircraft is a highly responsible business, however trivial the task. The body sections represent a major contribution from the West German side, which is entrusted with 37% of the total production program. The flat quilted insulation mats cladding the sections serve a dual purpose. They insulate against the minus 50 degrees substratospheric temperature and also against noise. The plane in the next bay is closer to completion. Kilometers of cable looms are being installed. This is a job for highly skilled hands. As soon as parts are finished, they're ready for testing. The aircraft is designed for a 20-year service life or 30,000 takeoffs and landings. But tests subject the aircraft to triple this, a total of 90,000 flight cycles. The rear section, the largest Airbus subassembly, is bent by hydraulic power. It is subjected to stresses such as the aircraft encounters in electrical storms. The only difference being that in this test, the load is many times greater than in any conceivable flight situation. All structural elements, the tailplane, landing gear and wings, receive similar punishment. A 90-minute flight is simulated in 4 minutes. Aging in quick motion. The physical link between the European partners is the Super Guppy, a very remarkable transporter. No other freighter in the world can compare with this cargo aircraft as far as cross-section goes. Four aircraft of this type, which was developed 20 years ago for the Apollo moon landing program, fly entire Airbus sections for final assembly at Toulouse. Guppy, the name of a tropical aquarium fish, seems less appropriate than flying whale. International cooperation on this scale would be unthinkable without the Super Guppy. It takes only 45 flying hours to bring all the Airbus sub-assemblies together for final assembly. Final assembly at Aérospatiale, the French partner in Toulouse. 5 major sub-assemblies, the power plants and hundreds of other components come together to make up the complete Airbus A310. Each major sub-assembly already contains all its ancillary systems, such as hydraulics, pressurization and air conditioning, and electrics. Section after section joins the final assembly. International Airbus Corporation has been running for longer than 10 years and has certainly stood the test of time. The accuracy with which sub-assemblies fit together is proof of it. The great bird slowly takes shape. The A310 cockpit design and instrumentation conform to the most advanced concepts. Push-button techniques and a number of newly developed instruments require 150 kilometers of cable laying in the cockpit alone. The last outwardly recognizable assembly phase is mounting the low-noise, low-emission power plants. The engines are derived from the same General Electric CF6 family of fan jets that power all the wide-body aircraft of the Lufthansa fleet. The aircraft is made ready for its first flight. Engine ground run. The first flight is preceded by comprehensive system checks, test after test, on the control surfaces, flaps and air brakes, rudder and elevators, spoilers and air brakes coupled. Then come the first independent taxiing attempts, still tethered as it were. A ground mechanic cooperates with the test pilot to ascertain its ground maneuverability. The unfinished passenger cabin contains 2 tons of electronics, 15 tons of lead ballast, and only 1 passenger, the test engineer. At long last, clearance is given for the first flight. The A310 lifts off into its element. The first of 30,000 takeoffs and landings in its roughly 20-year career. Takeoff performance is compared with the standard data: acceleration, rolling time, rate of climb. High-speed printers register the data for immediate evaluation. The same concentration in the cockpit. Test flights run to a rigorous schedule. 2 monitor screens relay cockpit information and flight data to the cabin. The results may look somewhat unfamiliar, but the specialist reads them like an open book. Like the wings, the cockpit with its CRT displays is also an innovative development. Individual indicators and their coordination to a mental composite picture are now a thing of the past. Here, information is processed and presented in its entirety. The artificial horizon is the dominant feature on the primary flight display. A vector marks the speed trend of the next 10 seconds flight. Speed limits are indicated by special markers. The navigation display offers 2 modes. Either it shows the familiar compass rose, or it shows track and position. This navigational aid allows a flight over the map to be simulated. One can fly as if with ground contact, but above the clouds and even at night. Another concept has been realized with the electronic centralized aircraft monitoring system. The pilots also use a CRT screen to check the status of various systems. Cabin temperatures, engine and fuel data, control settings, hydraulic systems, and electrics. Should a failure occur, the defective system is displayed graphically on the monitor. A further monitor functions like a digital memory. It displays the fault, shows in what order countermeasures are to be taken, and demonstrates how the failure affects flight procedures. The test flight routine also includes an automatic landing for which the aircraft is certified. 3 independently operating electronic systems guide the aircraft at exactly predetermined approach speeds onto its localizer course and glide path until touchdown. The power setting is automatically adjusted to match letdown rate and high lift surface settings.
400.
Radio altitude is announced by a computer-generated voice.
300. 200.
In poor visibility, autoland facilities are a boon to the flight crew, and the passengers can feel secure in the knowledge that they will reach their destination safely and punctually, even in fog.
30, 20, 10.
On its final test flight, the A310 covered the 1,000-mile distance to the MBB dock in Hamburg. On this flight, it was able to prove its economy, which in view of steadily increasing overheads, helps to keep it competitive. At Finkenwerder, near Hamburg, just behind the Elbe River Dike, the Airbus is given its final equipment and fittings. 25,000 individual components are brought aboard and installed: panels and bulkheads, baggage lockers and partitions, passenger address systems, galleys and toilets. Galley installation and wall paneling are the first steps towards interior outfitting. Preformed plastic panels are positioned. Accurate fit is essential here too, because subsequent trimming would take too long. And finally, the installation of the seats, 18 in first class and 193 in tourist. As at all previous construction stages, Lufthansa personnel supervise the progress and quality of the work. Not even the minutest detail is neglected in the interests of safety or comfort. Safety and comfort are just as important in the cockpit. Route-operated push buttons have replaced the laborious cockpit checklist preparation. The aircraft is ready for takeoff when all the lights are extinguished.
Okay.
Flight and ground crews, as well as passengers, have given the Airbus A310 a warm reception. The aircraft is meanwhile just as popular on the European routes as in domestic German service or around the Mediterranean. Further destinations in Africa and Asia will follow. The cockpit of the A310, with its 6 multi-purpose CRT displays, is just as much a trailblazer for the next aircraft generation as a decisive factor in the cost-effectiveness calculation. Never before have 211 passengers and 25 tons of cargo been flown on short and medium-haul routes so economically.
Dankeschön. Ja.
The aircraft no longer flies you faster, farther and higher, but the Airbus A310's superlatives are achieved in other ways: economy, silence and comfort. That may not be an Olympic motto, but it's not a bad one for our day and age. A standard for the new generation.